So this is paper 2 of just regular maths A-level from 2021, October. Let's just head into it. So common difference, well, there's 20 terms there and there's a difference of 8. So if we just do 8 over 20, we'll get 0.4, so that'll be our difference. You could do it fancier ways, but whatever. Hence find the sum of the first. Well, we've got this formula in the formula book, and we have n is 500. We've got a difference, which is d, is 0.4, and we have a, of course, is 16. And we can just substitute that into this formula here, I believe. And so the s of the first 500 terms is just going to be all this. You can type that into a calculator and you'll get your answer. Okay, so a nice easy one to start. State the range of f. That's all the values that f can be. So thinking about substituting things into x here, what range of things can you have coming out of it? Well, this is just an upside down quadratic, isn't it? Peaking at 7. So you can have any values less than or equal to 7, right? It just looks like this, and the top here is at 7, so you can have anything below that because the graph just continues forever. But you can't have anything above it, because of course you're taking away something positive. Like, this is definitely positive for the real numbers. So you're just doing 7 take away either 0 or something bigger. So yeah, we get this. Hence find this. Now you could actually compose g and f here to find g of f, but the easier way is just to work out f of 1.8 and type that into a calculator, and then do g of this. And that's probably the easiest way of doing that. So we get this, that's the answer. Find g inverse. The way that I do this is I let g inverse equal something like y, and then I'll flip the g to the other side, just like you would flip sine inverse when you're flipping that. It's just a function, so it flips and you don't have the inverse anymore. G of y is just this with some y's in it. I'm going to rearrange this for x, so I've cross multiplied out here, move some things over, factorize, divide. And of course y is what I decided g inverse of x should be, so g inverse of x is that, I believe. Excellent, so a couple of easy questions just to get started. Here we just need to follow log laws. When we're taking away two logs, we do this one divided by this one. So we'll have this, then of course we can raise both sides to the power 3 to remove this log and get 3 squared over here, which is 9. We can then multiply that over there and times both these things by 9. We can then of course just solve this using some year 7 maths. Question number 4. So small angle approximations are in the book. Good, so we have those. So sine theta over 2 is going to be approximately equal to theta over 2. We can just put that in there. Cos squared theta is going to be approximately equal to this thing squared, which is, I'll expand that in a second. And of course I can just times all that by 3 as well. So let's just put 4 lots of this, which is just 2 theta, and this together. So 4 lots of that is that's just 2 theta, like I said. And this, I'm going to expand this out. Just make sure you have this times itself. So it's 1 plus 1 times minus theta squared over 2 plus 1 times minus theta squared over 2 gives you minus 2 of them, which is just one of them because they're divided by 2's. And then of course plus theta to the power 4 over 4. And there's the 3 out here. This was 2 theta, like I said. You can expand out the 3 here. Now this term doesn't really matter because when theta is very small, it's pretending powers above squares don't really matter anymore. So we can just ignore this and we end up with that, which I think is exactly what they wanted us to have with the values that I've got there. I should have said, yeah, this is approximately, I think I'm right here. This is approximately equal to this, which is equal to that, and then is approximately equal to that, and therefore approximately equal to the very first thing. Yeah, I think that's fine. Question number 5, so very straightforward here, just some differentiation to start with. So 4 times 5, 3 times 24, and so on. Reduce all the powers down by 1. Do it again, and you get 3 really nice marks. Verify C as a stationary point at x equals 1. Stationary points are when dy by dx is 0. So when you put in x as 1, do we get 0? Yes, we do. Good, so that's verification. And then secondly, show the stationary point is inflection. So there's a couple of ways of doing this. You can put x equals 1 into d2y by dx. Sorry, that's the conclusion of the previous bit. You can put x equals 1 into this and you get 0. Now that's not actually enough to show inflection. What you need to do is then, well, one way of doing it, and the way that I was taught, was to differentiate again to get d3 by dx cubed, and then put in this point. And as long as that's not 0, then this is an inflection point. So this alone doesn't guarantee inflection, but as long as the next one isn't 0, the next derivative, then it is. Alternatively, and what the mark scheme actually wanted you to do was sort of draw a little picture and use a couple of values either side of 1 and show that the gradient is like positive just before 1 and positive just after it, or negative and then negative, of course, to show that. And then you can draw this little picture that says that the graph sort of does this because it's positive both sides or negative both sides and then 0 at the actual point. So that's what the mark scheme wanted you to do, but sure, okay, whatever. So here we've got some sectors in radians, so we need to think of our formulas for area and arc length in radians. I think area is r squared theta over 2, and arc length is just r theta, so that's nice. First it wants us to work out the size of angle AOB. Now, of course, this is just pi radians. 180 degrees is pi. So this angle is going to be, because these are all symmetrical, it says, this is going to be pi minus theta all divided by 2, or just a half of that. Good, show that the area of this, so area is what I said here. Show the area of the whole thing. So we've got 3 sectors to deal with. We've got this one here, which has r as 2r. And then we've got 2 lots, so that's this one that I just said with r as 2r, that's this one here. And then we've got 2 lots here of radius just being r, and then the angle being what we had before, and then of course over 2. And we just need to simplify this up. It's not too bad. These 2's obviously cancel. You get a half r squared pi, and then you get a half minus half r squared theta. And then here this becomes a 4 divided by 2 is just a 2, and we end up with this here, I think, because that's just a 2, and then we minus a half, and we get plus 1.5. Yeah, sure, that's fine. Good, so we have our answer, and then I guess factorize out. Oh, and we're trying to match the thing it has there. Good. Find the perimeter of the logo. So that's just arc length is r theta. Of course, arc length isn't perimeter. We're going to have to add in some straight sides here. But of course, if that's r, then this is just r, because that's 2r. So we just need to add in a couple of r's around here. So these are the arc length bits. So we've got 2r theta for this bit, and then 2 lots of r times this theta again for this one and this one, and then we just need to add in r and r and r and r to get the entire perimeter, so that's another 4r, and then again we just simplify it and we get some answer down there. Good, question 7 then. So we've got some stuff going on here. We've got a line that's tangent to a curve, so immediately thinking differentiation here to find gradient of curve, therefore gradient of tangent, so I think that's what I'm going to do. Good, so we differentiate this, we plug in the point x equals 5, and we evaluate that its gradient is 2. So therefore the gradient of this line is 2. I could work out the equation of this line by doing y minus y1 equals mx minus x1. Y minus y1 is y minus minus 13, which is plus 13. And then we can sort this out and we get this. That's quite cool because notice this y-intercept of minus 23. The curve also has y-intercept of minus 23. So these 2 points there are shared. And yeah, so we have that. We've done this. That was very quick. Hence verify. Oh, and we've done that. I've just explained 23 and 23. Yeah, cool. Yeah, good. So next bit, find the area R, of course. So what we'll do is we'll split this area upwards like this. There's more ways of doing this, but I split it up into a trapezium here. Well, I didn't really split it up. I just said there was a trapezium all the way around here, right? This is 13, this length here, because of that number there. So that's 13. And this, of course, is 23, as I've already said. And this is 5, because of this point here. So this area is 13 plus 23 divided by 2 times 5, which is 90. And then if I integrate this curve between 0 and 5, I'm going to find the area underneath the curve. Well, that's what we usually say, isn't it? But because the curve is underneath the x-axis, what you actually do is you find the area between the curve and the x-axis, which in this case is the area above it. So if I integrate this curve here between 0 and 5, I find this area, this white area around here. And so my plan is, once I found that white area by doing this integral, I can just do trapezium minus white area to give me r. So okay, let's do that. So we do this. It's just standard integration stuff. I'll let you just follow the maths if you need to. The zeros just all go away, which is really nice, and you get this. Now that's a negative number because the area is underneath the axis, and that's just what integration does to represent that. So I can kind of just ignore this negative for a second and just say, well, my plan was area of trapezium minus this white area, so just minus 37 and 11/12, and we get this here. Here's our answer. And yeah, that'll be that. So the curve C has equation this, show dy by dx. So there are x's and y's all muddled up here, so this means implicit differentiation. Of course, when we differentiate the x bits, it's all good. It's just 3px squared, and then here is a product. So we differentiate the x, differentiate that to get qy, because x just differentiates to 1, and then leave the x alone to get qx. Q is just a constant, right? So we're not bothering with that. And differentiate y for 1, but tag a dy by dx on because you've differentiated a y. And then here, this is 6y dy by dx because you've differentiated y again. 26 differentiates nothing. Group the dy by dx's, move everything else over, divide by that thing, and we end up with what they wanted us to get. Where these things are all integers. Good. Given that this lies on C, so when x is minus 1, y is minus 4, apparently, and the normal to this is this, find the value of p and q. So there's a fair bit to do here. Firstly, what we'll say, is we can substitute in -1 and -4 into the original equation, and that gives us some information about P and Q. So it eventually boils down to this. So that's the first thing we do. And secondly, the normal to C has equation this. So normal, we're talking about gradients, right? So let's rearrange this to see its gradient. So move the x's over and then divide by 26. And this is the normal. So that's not the same as the gradient of the curve here, this -19/6. That's the negative reciprocal. So I think the gradient of the curve is therefore 26/19. But of course, the gradient of the curve is dy by dx. So 26/19 is this expression here. And of course, that's only the case at the point -1, -4, because that's the normal at that same point. So this here is 26/19 if x is -1 and y is 4. And of course, after we sort all of that out with doing some algebra, we end up with another equation in P and Q. And so now we've just got a simultaneous equation. You could either just type this into a calculator, right? That calculator solve that. Eventually you'll get this here. And that's exactly what I did, apparently. Just typed it in. Okay, excellent. Question number 9 then. So first thing to deal with is this annoying cos thing. So when n is 2, you get cos 360, which is just 1. And when n is 3, you get cos 540, which is -1. And then when n is 4, you get +1 again. And because you're going up in 180s, sorry, in 360s, no, you're not. You're going up in 180s. I'm being an absolute idiot. Because you're going up in 180s, it's just going to go from 1 to -1 to 1 to -1 and so on. I don't need to prove that. This is clearly not enough marks for me to actually have to prove that. I'm just going to say that that's true. So each term here is going to be 3/4 to the 2, minus 3/4 to the 3, plus 3/4 to the 4, minus 3/4 to the 5, and so on. Right? Because that all cos is doing is just putting a plus or a minus here, alternating. So we have this to deal with. Now this is just a geometric series, right? We've got a first term 9/16. We've got a common ratio of -3/4, right? There's a 3/4 here in order to make this power go up every time, and there's a minus here in order to change the sign every time. And now we know the sum of a geometric series to infinity. It's this one here, as long as the ratio is less than 1, which it is. Well, the mod of the ratio is less than 1, which it is. This is 3/4. That's fine. So we can just plug that in and type that into a calculator, and you get your answer. Quite an interesting question. I actually thought it was one of the better ones on this paper. So okay, here we have a axis to do with. Oh, okay, we'll start here actually. Show this thing can be written as this thing. So take log to base 10 of both sides. Log laws, because this is a product here, so you can do log of this one plus log of this one. And then another log law says this b can jump down, and we have our 2 marks. Good. And now here we have a graph where its y-axis is this, notice, and its x-axis is this. So actually, if you were just to replace that with a y and that with an x, this would read y equals bx plus this. And that sounds like the equation of a straight line, right? Where b is the gradient and log 10a is the y-intercept. So that's what we need to ascertain from this. And then, of course, we can actually work these things out, right? We can work out the gradient from these 2 points by doing a little gradient triangle if we want to, and we get this random number. I think I've rounded that, actually. And then we can work out the y-intercept. I mean, there's a few ways of doing it. I just actually straight up worked out the equation of the line, apparently. Y minus y1 equals mx minus x1 is what I did, apparently. And I found the equation of the line, and then I put in y is 0, I guess. No, I didn't. Oh, when I found the equation of the line, of course, because of this 0, there was no rearranging to do. This is just the y-intercept right here. So log 10 of a is this, raise both sides to the power 10, or 10 to the power of both sides, I should say. And we get a as this, and we have our 2 numbers. And I actually lost a mark here looking at the mark scheme because I didn't bother to write this out, which apparently you must do, which I think is dumb. With reference to the model, interpret the value of the constant a. So we need to read this carefully, right? So with reference to the model, so what's a doing here? Well, log to base 10 of a is the y-intercept. And I'm stalling for time because I can't actually remember how I thought this through. So you might want to give me just a couple of seconds. I think what I eventually realized was, okay, a is to do with the y-intercept, right? And when does the y-intercept happen? Well, it happens when log 10 of L is at 0, which means L is 1, right? Because log to base 10 of 1 is 0. And then we look back here and go, okay, well, if L is 1, this b doesn't do anything. 1 to the power of anything is just 1. So a is the time the pendulum takes to swing when L is 1, is what we'll say. And actually, that question comes up a fair bit, and you might have just seen that kind of question before, so you could just answer it. But yeah, anyway. Here's a mod graph. I both liked and disliked this question at the same time. I just thought it was quite interesting. This is the graph sketch of this graph. That's good. This is just a straight line, right? So 2x minus 3k. But then, because it's modded, you just turn it as soon as you reach the x-axis and goes back up here again. Sketch the graph of this. So firstly, I just sketched minus this mod, which just looks like this, because it's just minus f of x, isn't it? So you just flip it in the x-axis. And then this is the same as this thing plus k. But plusing k just moves the graph upwards. So I think my sketch will look like this. And I'll have a top point here of, well, I need to find the x coordinate of this here. And that's just when this is 0. So we solve that and we find x is 3 over 2k. And of course, all I've done is I've flipped it over, then moved up k units. So this point here, I think, is 3 over 2k, comma k. So that's cool. It also wanted any other coordinate axis, so I need to find these 2 points here. Now, I think I've overblown this. I just solved the function to be 0 to find roots, of course. That's what you do. F of x is 0 when you're on the axis. And then I moved this thing over, and then I just squared both sides. You can do this in a much easier way than this, but this is just how I did it. Divided everything by 4, and then if you take the k's out, you make this equation, and you just think, well, if that's factorizable, then this is. Because all I would have to do is put a k in. So this is factorizable because it's just minus 2 minus 1. So this becomes minus k minus 2k. And then the k is just put in here. And so we have roots at k and 2k. So k there and 2k there. And then this point down here happens when x is 0. So we go into here and we set x to be 0, which gives us mod of minus 3k, which is just 3k. Minus that is minus 3k, plus k is minus 2k. And I think we've got all of that done. Okay, find in terms of k the set of values for which that is bigger than that. Okay, so I've got all of this labeled down. Don't know what this rogue k is doing. I assume I'm going to use that later. So we have a line here of x minus k. So that's a gradient 1, y-intercept of minus k. Now, minus k is a little bit further up than minus 2k. So it looks a bit like this. And notice as well, when x, in the line y equals x minus k, when x is k, y is 0. So I think this point here, k, is shared here. So that's kind of cool. So we definitely have a intersection between this curve here and the line at k. Now all we need to do, this is really asking when is our mod graph here, when is that higher up than the line here? And it's going to be higher up between k and this value here, and I just need this value here. Now again, you could just set these two things equal to each other and find the intersection, but actually what we can say is, for this part of the line, just this part, which is all I care about because that's where it intersects this line on this time, because I've already found that intersection. For this part of the line, that was the reflection of this part of the original line. And this part of the original line is just 2x minus 3k. It doesn't need the mod, right? This mod function does nothing while the line is doing this. And then when the line reaches there, then the mod function starts doing something to turn it the other way. But right here, this line is just 2x minus 3k. So when I flipped it over, it just became minus 2x minus 3k in brackets, I guess. And then we added k up. So we actually don't need the mod function here to compare it with this line, to find the intersection between this and this, because the line is just acting normally here. This is just the original line. So I can just say this, and then I can solve that, and I'll get x is 5/3 k apparently. And then I can say, well, okay, the solution is between k and 5/3 k. It wants it in set notation, so we just do that, I guess, and we have our answer. And then find the minimum point of this. This is just a lot of graph transformations. So f of x has a minimum 3 over 2kk. So f of a half x stretches the graph out by factor 2. So this 3 over 2 becomes 3, right? And then this k doesn't change. So this f of a half x is going to have minimum, a maximum, I should say. Why does, it's a minimum because of what happens later. Right now it's a maximum of 3kk. Because this one's going to double and that's not going to have anything. When you times by 5, that stretches the graph vertically, so that coordinate changes to a 5k and this coordinate doesn't change, so that's good. And then we flip it over, which is why it's going to be a minimum. And when we flip it over, we flip it in this axis here. So this coordinate's going to become a negative, this coordinate again doesn't change, so that's just going to become a minus 5k. And then we can just think of this as adding 3, because this is the same as this, plus 3 on the end instead. So we can just think of moving it up by 3, which just increases the y coordinate by 3, and we'll have our minimum point here, which I've written out more carefully there. Okay, question 11 is just a nice substitution question. Firstly, we derive both sides of this. We get this. This is x to the power of half. So the half comes down, lower it by 1 to get that. We can rearrange this a little bit. I've put this back into this to make it look more easy for me to do that. Of course, 1 plus root x is just going to be replaced with a u. X I need to get, so let's take away 1 from both sides, which is convenient because that also helps me to substitute that into there. So this is going to be u minus 1 eventually. Square both sides to get this. And I also need to change the limits. So I can replace that with a u, replace that with this, replace this with that where root x is this. But I also need to change the limits. So when x is 16, 1 plus root 16 is 5. So I've also written there, sorry, I've replaced that there. And then when x is 0, 1 plus root 0 is 1. So we have this integral to do, and of course this times by this makes this a 3, and you can put the 2 in the front. I would prefer to put the 2 here, but who's judging? Hence show this thing. Now, there's probably some smart things you could do here. I didn't do any of them. I just expanded out this top length here because I just know this expansion off the top of my head, so I knew it would be super quick. And then I just divided each of these terms by u one by one to get to here. And this is definitely integrable. U cubed over 3, 3 over 2u squared, 3u, and then log u at the end here. 1 over u integrates to log u, remember. And then we can put the 5 and the 1 in, and we'll end up with this, and then we can sort it out in the calculator, and we get this, and that will be the answer. Good. Cool. So next question. Find dy by dx with parametric equations. So we just differentiate both these things with respect to theta. The first one gets this. And the second one, I chose to write this as sine theta to the power minus 3. Because now I can just do chain rule. So, okay, differentiate this. You bring the minus 3 to the front. That goes to a minus 4. And then the derivative of that is cos theta. So I think I end up with this. And now dy by dx we could say is equal to dy by d theta times d theta by x, because we could sort of pretend these cancel, and we'll get this. Let's just flip this over to make that, and then just multiply these two things together, and we'll get this. I think all I did was put this sort of into here like this. And because it just says an expression, I don't think I have to do any simplifying to this at all. I think this is an expression, so I'm just going to go with it. Hence, find the exact value of the gradient to the of the tangent to c at the point where y is 8. So when y is 8, we have dy by dx, but it's in terms of theta. So having y equals 8 doesn't help. So put y as 8 into here, and then of course we can raise both sides to the power minus a third, because if you raise this to the power minus a third, minus 3 times minus a third goes to 1. So we just get sine theta to the power 1, which is sine theta. This is of course 1 over the cube root of 8, which is 1 over 2, and this of course is pi over 6 if you know your exact values. We only need to know that value because of this limit here. There's no alternate values. Put that into here, and I mean you can just type into calculator and you'll get your answer of this. And good. I think we've only got 2 questions left. I think it's quite a long paper. These papers are quite long. We have some information here about a tank that's leaking here. I don't know whether it's leaking or it's deliberately. I don't know. It's a tap. Sorry. Yeah. So it's just sure. So water is going in at this rate and going out at this rate. So therefore, the rate of change of the volume in the tank, which is dV by dt, is this minus that. So that's our good starting point. We also, of course, have the volume, just V in the tank, is just h times 3 times 8, which is 24h. And my plan is to use this. So we did something similar a couple of questions ago, didn't we? dV by dt I can say is dV by h times dh by dt. Of course, I can get dV by dh because that's just 24 from there. And dh by dt is the kind of thing that they've got in here. I know dV by dt, it's in there. So let's put this in there. Let's put this in here, and we'll get this. And I think they just times everything by like 50 or something to get this. I don't know. Sure, whatever. So we have this. That's done. And then show according to the model we have this. So they're essentially just asking us to solve this differential equation. T is 0 and h is 2 is what this gives us. So of course, when we solve this differential equation, we're going to get a constant when we integrate. So what I did was I divided everything by 24 minus 5h, and then times everything by dt to get this. And now I can integrate both sides. This is not the easiest integral to spot, but it is just log of this thing at the bottom times by minus a fifth. Because if you think about differentiating this, you differentiate this for minus 5, which cancels with that, and then you just have 1 over this thing here. Maybe this should really be in mod signs, but it doesn't matter, I don't care. And then the 1200 doesn't really do anything. And then you plus c because you've integrated it, and then the integral of dt is just t. We can substitute in this starting figure here, that when, I simplified that. So when t is 0, h is 2, and we can do some maths, and we end up with this. And yeah, we can write that as our final line into the original. So I just put this c into here, I think this one here, to get this. Okay, so that's that, except we haven't rearranged it for h, right? So this is a solution to this, but we haven't rearranged for h, so let's do that. It's quite a long process here. Divide everything by 240, I presume is what I did. I actually just swapped these over. Okay, sure. And the reason I did that was because now I can see that there's this log minus this log means this divided by this in the logs. I also divide by what, 240, finally. I can now raise both sides to the power e to cancel this and get this there. I think at this point you can just flip these over essentially to put a minus here. Which you get a hint with because there's a minus there. Or you can think about just moving the 14 up to the top of the other side, and then because you're dividing by this, you can put a minus there as well. So a couple of different ways of thinking about that. You can also cross multiply and whatever, but there's a few ways of getting here. And then, of course, just take away 24, or add 5h and then take away this. I don't know what I did. I took away 24, and then I divided by minus 5 to get this. And that's that. Good. Given the tap remains open, determine according to the model whether the tank will ever become full. So that's my solution here from this. Now, ever become full. So we're looking so let's pretend a lot of time passes. So let's put a very large value of t into it, like a really large value. 10,000 isn't that large. I think I just got bored of typing. E to the minus a very big number is basically just 0. And 0 times this is basically just 0. So you just end up with 24 over 5 minus 0. So when t is very large, h is just 24 over 5, which isn't 5, right? That's 4.8. So the tank, even if it reaches some equilibrium, right? After a really large amount of time, because the rate of water flows out faster when the height is bigger, it reaches this equilibrium point where at a certain height, the water going in is balanced with the water coming out, and you just never fill it up. So yeah, cool. Okay, so we've got some R formulas going on here. So R is just root this squared plus this squared, which is a minus 1, which I can just write as 1 because you're squaring it anyway. So R is root 5. And then alpha is going to be tan inverse of 1 over 2 here. Now, a lot of people make a mistake of putting a minus here, but because of this plus here, it's actually fine. You can maybe see why if I do it properly. Like cos of theta plus alpha using the compound rules in the book is cos theta cos alpha minus sine theta sine alpha. I've just expanded out the R to both as well. And then what we do here is we compare, because the alpha is a constant, right? The alpha is a constant. That's the thing I think a lot of people don't get about this. Alpha is just a constant, which means cos alpha is just a constant. So if this side is to be always equal to this side, because cos theta is actually a variable, because theta can change, we just need the things attached to cos thetas to equal each other. So 2 needs to equal r cos alpha, and minus 1, same logic with sine theta, needs to equal r sine alpha. Of course, there's a minus 1 here and a minus there, so those cancel. And then we get this statement here by just doing this divided by this to get r's cancel. So it's just tan alpha equals 1 over 2, and then tan inverse of 1 over 2. So that's where I got this from. And that means I can write this thing here as just this with a root 5 and a thing there. So that's good. Okay. So that's that bit done. Using the model, find the height P above the water level. What is this talking about? The maximum height, sorry, the maximum height. So when we're looking at this, sorry, first I need to, yeah, this has been a long paper, sorry, I'm getting tired. This is all well and good, but it's not the equation for h they've given me about this wheel here. So let's double everything to make the 2 and the 4 match. Let's add a 3, and let's replace theta with 0.5t everywhere. And so now h equals this thing here, which is much easier to work with than this thing here. And now we can answer this question. The maximum height, well, look at this here. Cos is a maximum at 1. Right, that's the biggest cos can ever be. No matter how complicated you make the expression in here, cos is not going to be bigger than 1 ever. So the maximum the height can be is when cos of this is 1, which means you just get 3 plus 2 root 5. So that's the h max. And then when does that happen? Well, it happens when cos of this is 1. and then we take a cos inverse and we get these answers here. We can take away 0.464 from everything, and then we can double everything to get this. And now time can't be negative, so the smallest or the earliest possible maximum height is at 4 pi minus 0.928, which is this number here. P is below the water level, so there are 2 times P is on the water level, here and here. P is below the water level for a certain amount of time. Find that time. So if I could find the 2 times it's on the water level, I could just take the larger time away from the smaller to give me the total time that it kind of exists there for. So okay, let's solve this thing equal to 0 to find when it's on the water level, because of course when h is 0 we're at the water level. So let's solve this here. Take away 3, divide by this, do cos inverse. Now cos inverse of that gives me this number here, 2.3, which is less than pi. So if I do pi minus that number to find the difference between this and that solution there, then add it onto pi, I'll find the other solution, which is what I did here. So that was pi minus this, get some answer, and then add it to pi, and you get this. So that's just symmetry stuff. Take away this from both sides, double it again, and we get this, and we do the large value minus the smaller value to find our total time in between. And we have that. In reality, the water level may not be of a constant height, so the water might be going up and down a little bit. Explain how the equation should be refined. Well, look at the equation for h. It's stuck at an initial sort of bit of 3 here. So if we just varied 3 a little bit, or if we found some way of making 3 vary with the water, if there was some equation for how the water varied and replace that with this 3 here, then we'd be done. Because this 3 essentially just represents this distance, I think, from here to here. So yeah, we just need to vary t a little bit. Sorry, vary this 3 somehow, and we'll have a good way of replicating the variance in the water. Good, I think that's about it. So thank you for watching, and I'll see you next time.